RAG is seemingly everywhere. There's dozens of systems people build RAG with, maybe more than that at this point. Closed source, open source, lots of options. But in the real world, dealing with real businesses, especially regulated industries, you have to take it a step further. You have to build RAG where their data already lives. We're not talking about the cloud. We're talking about RAG on premises. We're talking about RAG in a data center. It's a next level of difficulty, and there's lots of different things you need to learn. So in this episode of RAG Masters, we're going to take you through it. Hi, I'm Neil.
And I'm Daniel.
And welcome to another episode of RAG Masters, the world's only show on Retrieval-Augmented Generation. We think it's a pretty cool topic. I don't know. I thought there'd be 20 shows by now. There's just one, but that's okay. Today we've got a great topic and a special guest. This topic is near and dear to our hearts here at EyeLevel because it's what we focus on, but we're not the only ones. And we're going to talk about RAG on premises, how to actually build, test, and deploy RAG in data centers, maybe even an air-gapped data center. We're talking about really how things work in the real world when you deal with regulated companies. This is not for Joe's Flower Shop. This is when you want to build RAG for financial, healthcare, logistics, military, government, etc. High-end applications where, frankly, they've been securing their data for the last 30 years. They're not about to send their data flying across the internet just because you got a cool AI feature, a cool RAG platform. In fact, just the opposite. You have to bring your AI and your technologies to where their data already lives. And that creates a whole new set of challenges. So today we've got with us a special guest, Ben Fletcher, the chief scientist and CEO of EyeLevel. And, Ben spent, 20 years at IBM building out enterprise-grade AI at scale in exactly the kind of environments we're talking about. One of the original founding team of the Watson Group at IBM, served several tours of duty in that environment. 21 patents to his name, many of them in mobile security and VPN architecture. Security is another huge, huge issue for building RAG on premises. So there's a lot to talk about. And you've been very silent, Daniel, actually. You usually have something to say.
Yeah, as boss music comes in. I'm excited because I am usually the expert. If you go into the EyeLevel blog, you'll see some things that are written by Daniel about on-prem. They're technically written by me, but they're all from Ben. Written by me. I'm a data scientist, right? So I'm excited because this time I'm going to be kind of the one asking a lot of questions too. I think I'm excited to learn about on-prem. I know it's challenging, but it's one of those difficult problems that you have data science, but then you also have inferencing and you have hardware, you have networking, you have scaling and provisioning. It's like the entire tech stack converges when you go to on-prem. So, I mean, let's bring them on. I'm super stoked to get started.
Ben, come on in. Ben, how are you?
Good to see you guys.
Good to see you. Good to see you. Welcome to RAG Masters. Good to have you here.
Thank you.
So let's probably jump right into it. RAG on premises. Before this show, you were saying, well, there's like 200 things you have to do RAG on premises, right? But maybe go a little bit higher level, and we'll dive in. Like, what are like the three most important things you think about to try to deploy a RAG on premises system?
I'll go even one level higher and start with why it's something you should think about or have to think about. So when you talk about massive scale and needing to architect systems for massive throughput and scale, traditionally that's been based on things like number of website visitors of a website. So like companies like Facebook, Twitter, they deal with millions, billions, trillions of requests per second. And that kind of throughput of requests and kind of load on your systems, it creates unique challenges. And those challenges, again, you only experience in the biggest companies and have to think through and deal with. With RAG, the load, the requests are coming from documents, and a single document, 200 pages, can generate 1,000 requests per minute on a RAG system. So even if your law firm has 3 lawyers, you've probably got 100,000 documents, probably 10 million pages. To turn that into RAG data would generate hundreds of millions of requests. So doing RAG, even at the smallest scale, creates the kind of load problems on a system that you only traditionally would see at the biggest consumer companies.
Right.
It's really like an existential AI problem. It sounds, because like I heard this anecdote, like, at Facebook, they used a monolith. If it's good enough for them in the beginning, it's good enough for you. Just, you can build up your application, deploy it on one container, and then scale it up, and you're fine. That's like the modern one of the modern paradigms of application development. And it's got up to a certain point, and then once you have like 1 billion users, then maybe you have to deal with provisioning, and you could start with microservices, whatever. But really, the point is, like, when in normal application development, you can start small. What I hear you saying is, when you're in like the RAG world, but also kind of the AI world, and you're dealing with AI generating a lot of information that you then need to sort through, the loads become so much more significant that you really need to start from the beginning with that sort of enterprise grade scaling and provisioning. You don't like build up to it over time. Does that track? Is that kind of what you're saying? You kind of need to start really sophisticated from Jump Street because of all of this traffic.
Well, like Facebook, one of the fastest growing consumer websites maybe ever, they started with 10,000 users, probably generating something on the order of 100 to maybe 1,000 on the upper end requests per minute on their servers. It's the kind of load that you could run on a laptop or a single server and support. And as they grew, more users, it happened over months. They were able to bring in more money because of the number of people using their product. They were able to scale their team and their skills and their servers and systems. With RAG, it typically goes something like, I'll try a couple documents and see what it looks like. Okay, now I want to upload a file folder. So average file folder might have 20 to 100 files. Average file is about 20 pages. So you're at 2,000 pages of documents pretty quickly, which would generate 10,000 requests if you were to try to process them through any kind of RAG pipeline, ingest pipeline. You're already hitting, the kind of scale that a Facebook hit in terms of like the number of requests you're putting against your system in your second test, which might be 10 minutes in. You don't have the months of time to build the engineering skill up to the load to process any amount of knowledge into a RAG database creates a load problem very quickly that in other paradigms like a website you don't experience so quickly. Anyways, the skills that it takes to architect systems that can handle that kind of load, process a file folder of documents and have it not take 8 hours to do. The skill set to create a system that can do that is just not widely available, because again, the people who have traditionally dealt with these problems worked at the biggest internet companies.
So how do we think about it? How do you think about it when you're trying to architect a RAG system that has the capacity to handle that throughput, and in particular can do it on a on-premises data center?
Yeah, a production RAG system is like any other production consumer scale cloud system. So it's the most popular paradigm is to create a set of services that are deployed like microservices, have them communicate with each other as if they are independent services using APIs to communicate, or possibly some kind of task queuing management system. RAG is really, the architecture of a RAG system is really the same architecture same ideas that would go into like Netflix, building Netflix from scratch. There's one unique aspect to RAG that a Netflix probably doesn't have to deal with, which is that in an advanced RAG system, you're adding in some kind of LLMs that are going to help, or models, and could be a layout model, a table model, but you're adding a microservice that it needs to be able to run models at consumer scale. So you're adding complexity of running models on a GPU and having them responsive enough to participate in this consumer scale pipeline. It's a special kind of microservice that I think is unique to AI, but otherwise the design of an advanced RAG system is very, very similar to what Netflix is doing, for example.
This is fascinating to me because I didn't even think about this until now. We've been talking about RAG for so long, and I've tackled it from so many angles. And the model hosting is such a bear within itself. Because if you're doing RAG with LangChain, and then you're using OpenAI for embedding, you have to parse your documents and then send them out and all that jazz. So now if you're trying to do it all locally, you're trying to do it all within your premises, you can't be sending data to OpenAI. You have to be basically building your own embedding model, or grab it from Hugging Face or something and then put it within your premises. So that's the hosting aspect. But this idea that not only do you have to host a model, you also have to deal with this enormous amount of scale that you took for granted when you were sending data to OpenAI it kind of doubles up the issue to me, because it's not just you need to have a compute system that can store models. You also have to deal with probably significantly more throughput than you were originally imagining while doing that. So almost immediately you have to be really good at really, really, really good at hosting these models so that you're getting the performance that's required to do it in an economical way. Does that track? Does that do you think is that one of the cruxes of this problem?
Well, it's really a problem if you have any kind of latency requirement on processing a document. So if you're running it on your laptop, you can kick off whatever LangChain or whatever, and come back 4 hours later and you don't care, then this isn't a problem for you. But if you're trying to spin up a production system where maybe an employee can upload a document and have it become part of your RAG database, and have it responsive in sub 1 or 2 minutes, have it through your pipeline and available in your searchable in your RAG database, then you have to start thinking about these things. And yes, with an embedding model, you're going to have the challenges if you're hosting it on your own, that OpenAI has taken away from you. If you're using a LangChain, and my knowledge of LangChain is dated about a year, but a year ago when I attempted to use it at production scale, there was no concept of decoupling tasks within LangChain. It was pretty much call the document loader and point it at your vector database and hit go, and it just appeared there. So for example, the default, at least at the time, ETL was unstructured. It's what was processing the files within that folder, and then the separate system, the vector database, was receiving the embedded vectorized version. So there was a vector call in between. It's by default to OpenAI, to the open embedding models in OpenAI. But let's say you wanted to use your own embedding models. I believe there's a way to change the settings to call a third-party API, but so in that way it is compatible with you hosting your own embedding model. But then let's say you wanted unstructured to run more efficiently. So what's happening within unstructured is there's a OCR model in the default mode. It was Tesseract a year ago, There's a table layout model. A year ago, it was a fine-tuned version of one of Microsoft's models, and they just run as one monolith. At least, again, in the default settings a year ago. And so when we did this a year ago, the layout model inference times per page averaged 10 to 15 seconds on a laptop. The OCR is relatively fast at 2 or 3 seconds per page. And we calculated, if we wanted to run 100,000 pages on our laptop, it'd take a month. if we just ran LangChain as it was configured by default. And again, it's because the primary culprit was the table detection model, which runs very slow on a CPU. In order to get it to run at a more reasonable amount of time, we ran LangChain on a GPU machine. We had to configure it to recognize the GPU. At the time, there was it involved modifying the source code.
I think it took like a week, right?
Yeah.
Like it sucked. It was mostly you. I didn't even know how to do it. I'm a data scientist, but I'm a developer. But it was like serious low level stuff. Like I've been a developer for a while, and it would have taken me probably a month to figure out how to do it. If you didn't already have like an absurd amount of experience deploying models at scale via a variety of frameworks, I imagine it would have taken you significantly longer than a week to do that configuration. And that was just to get the parser in LangChain working at scale for like 100,000 documents. And it still was kind of slow, if I recall correctly. This isn't a dog LangChain. It's just when you're actually deploying these things on your premises at scale, every single part of the chain, the parts that you haven't even been thinking about, when you have parsing, you have chunking, you have turning into a vector database, you have storing, and then you have querying, and then you have passing to the language model, augmentation, all of those steps in the classic RAG pipeline. What I hear you saying is every single one of them has weeks, if not months, of very senior work to get to the point where it is scalable. And if I understand correctly, that's really one of the major differences between EyeLevel on GroundX on-prem and basically every other solution that you can run on-prem is that we've done that pre-configuration.
Yeah, I guess the short version is that LangChain abstracts out what should really be 4 microservices run independently, and there was really no way at the time to decouple them and even run them as separate microservices. Specifically OCR and the layout detection model. The detection model runs most efficiently on a GPU machine. OCR Tesseract runs really well on a CPU. And so just decoupling those two things and running them on the optimal machine as standalone microservices is what it takes to get this thing running at production throughput. And there was just no way to do it at the time. We ended up just running everything on a single GPU machine. So like the systems are just not architected to run each process on the ideal infrastructure as a standalone microservice, which is really key to getting this throughput to work at production scale.
And nor could they really. Like if we think about it, like what is LangChain? It's an open source, framework for open source development. It's not like, obviously, but it's designed for people to hop into AI and be able to build chains of applications that kind of run, locally within a single system. It's kind of it's a really quick set of tools that someone can use. It would be like saying that that you expect, I don't know, like addition and subtraction to be able to be distributed easily in, like Python, like sum and division to be distributed across many systems. Like the point of addition, subtraction in Python is to add numbers together on your computer. The point of LangChain is to do a chain of operations, on your computer. And I think it's kind of funny that, it's really easy to make a Twitter demo, and rightfully so, because it's designed to be really quick to be able to chain stuff together. But then when you want to deploy it at scale, it's not just saying take take Edition and broadcast it over 30 computers. Now you have to have like Kafka, and you have to have like, Kubernetes, and you have to have like deployment, and you have to have load balancing and load scaling, and you have to have distribution. You don't just take this simple operation and then just on like 30 computers. Like it's a lot of work to do that. I think that makes a lot of sense.
I want to switch gears a little bit. Let's be nicer to LangChain.
Yeah, it's cool. There's a reason Python has Edition and it runs on your computer. There's a reason LangChain exists and it can just do simple operations.
Good product, people use it.
It's not a dig. It's just, I think a lot of people try to push it really far, and they certainly can. But it's not a simple operation.
I just want to get us to maybe more practical advice about how engineers, maybe Ben, how engineers should try to think about building these systems. What are the big things they need to really spend some engineering time on, like load balancing and caching and metering and auto scaling, some of the things you talked about prior with us. Give some developers some practical advice about how they might build these things. How do you approach it?
You've got to think about the discrete tasks that occur in particularly in the ingest. It's really the ingest that has to be really well thought through. Mm-hmm. And again, this is not a criticism. None of this was a criticism of what people are doing. I just don't think people approach this with the understanding that they were going to be dealing with massive concurrency throughput issues from the start when you're talking about uploading a bunch of documents to a RAG database.
Yep.
And so you've got to think about it in terms of the discrete tasks that occur through your pipeline. In an advanced RAG pipeline, it starts with some kind of OCR, layout, detection. Those need to occur independently. OCR typically runs most efficiently on a CPU machine. The layout detection models typically run most efficiently on a GPU machine. And then you pass it downstream to something that's going to operate on it. In our system, it's a bunch of agentic processes. These all run relatively lightweight resource in terms of resource. So it's, a lot of CPU is involved.
Uh-huh.
And then in our system and possibly other systems, we do towards the end of the stream, the most resource intensive processing where we're running our agentic prompts against our hosted LLMs. And that is by far the thing that has taken the most time and consideration, because again, the unique part of this is the adding in LLMs and needing to have them available as consumer scale microservices. The rest of the pipeline has to be consumer scale. I said these problems have been thought through and solved for mostly websites.
Yep.
Companies like Netflix have dealt with this problem for years and have solved it. What's new, in addition to these very advanced cloud architecture, system architecture kind of concepts that are fairly well understood, is having to do it with AI models, and that occurs downstream. They should all be independent microservices that run on an ideal compute stack, and maybe it's just simply decoupling CPU and GPU. Even doing that would allow you to get from 30 days to do 100,000 pages down to at 8 hours or less.
But the GPU itself matters, right? I mean, which GPU you're using, and then how you
that's right.
Efficiently talk to that GPU is very specific, right?
That's right. So let's say you're running super efficiently with like Ollama or a Llama CPP. On the high end, you typically can see 10 to 20 tokens per second, which, if in an average page of text, there might be 800 tokens. So if you do the math, you're really talking about 40 seconds per page.
Okay.
If you're running a page of text through a model running on a CPU, even running on the oldest GPUs that are available, like in an Amazon, you're going to get up to 40 tokens per second. Okay. So you can cut that time in half simply by running on a GPU. As the more modern the GPU is, the more modern the libraries for inference are that can leverage. You can leverage on the GPU things like flash attention too, and you can get up, with an H100 up to 2,000 tokens per second, which is why H100s are in such high demand for so many different kinds of, model tasks. It's just, how the more modern the GPU, the more text you can process more quickly. But even the lowest end GPU is going to be better than a CPU.
But sure, but you can, basically you can pay your way out of a problem. You can just say, look, I'm going to buy the most expensive GPUs in the world and stack them up in a building somewhere. And some people do that. But I think you were telling me that even regardless of which GPU you're using, you have to write some code to use it efficiently so that basically you're not wasting all that money on whatever you spent for chips.
Yeah, there was a good comparison that was done of the different approaches to doing inference on a GPU. They tested something like VLLM, Tensor RT, and then working really low level with the drivers and the card. And they basically found, this was an A100 that they were testing on, and I forget which I think it was Gemma 3. And they were testing the token throughput speeds of these different frameworks for doing inference. And they found that, VLLM took 30 seconds to get Gemma 3 running on, and it was doing 600 tokens a second. Tensor RT took 2 hours to get set up, and it could do 700 tokens per second.
Mm-hmm.
Being low level and operating at the driver level, writing your own code that leverages, very low level operations directly off the GPU, tuning the model for the GPU could get you to 1,000 tokens per second, but it could take you, when we did this one time, it took a month. So it's, there are frameworks that get you 60 to 80% of the way to the most efficient use of the GPU. So it's not necessarily, it doesn't have to be, a month of time to get a model to run as efficiently on a GPU. Now there are pretty good frameworks that do a decent job, but it's still, not a simple thing.
So how do you handle something like load balancing? So you got multiple, now you've got a lot of scale. Now you've got multiple machines running. How do you think about load balancing in a RAG pipeline?
Yeah, so as a shorthand, if your pipeline is a series of microservices, I'm assuming that you are, doing some kind of load balancing, auto scaling of those microservices. You have an element of caching. You've thought really carefully about when you're reading and writing from a database and when you're reading and writing from a cache. And I'm just assuming those things, and that's true of every microservice in your pipeline, of which in an advanced RAG pipeline, there should be at least 2, as I said, something for GPU processing and some for CPU processing. When you start talking about running models at massive scale as a microservice, then you still need those same things, the load balancing, the auto scaling. In our system, we typically expose our models as an asynchronous service. So that every request gets processed eventually. So we've thought through everything in our pipeline to allow us to do that as an asynchronous process.
Mm-hmm.
And then our model microservices pull requests off a queue basically as the GPU comes available, and in that way we're always running as close to maximum efficiency on the GPUs as possible. But that's an extra consideration, because the GPUs are 90% more expensive than a CPU server. They're way more expensive, so you really spend a lot more time thinking about how I can use the GPU the most amount of time. And for us, that was creating an asynchronous microservice, having it scale up and down, creating a metrics that allow us to predict that there's going to be a bigger demand
for
GPU. When a file gets uploaded, trying to predict how much GPU time that's going to take, and so that you can spin up new GPUs on demand and always be running 80% efficient on GPUs. I would say in our system, probably more than half the time we've spent thinking about the architecture has been about how we can maximize using the GPUs.
I think this kind of hinges on part of the idea that GroundX uses LLMs, VLLMs, and generally approaches RAG differently than many other RAG approaches, right? Like usually you just chunk and you send it to an embedding model. So then you embed maybe a paragraph as a vector, and then you do vector comparison. But there's a lot more operations that require VLLMs, LLMs, and maybe other AI approaches. Can you give us a breakdown of the different types of AI models that are in GroundX and kind of how they kind of get balanced throughout the system?
Yeah, so even in the example you use where it's not GroundX and you're using embedding models, the embedding models have to be thought through in the same way that I just talked about in our own pipeline, because they're models. They run most efficiently on a GPU. They will be the most expensive part of your pipeline, and so even in the example you gave, you have to think through it. In our pipeline, we have we basically vectorize in real time. We use a set of hosted models. When a query comes in, a search query, we do a RAG database search. That's a hybrid search based on keywords and a semantic understanding of the text. And then we send the chunks that are retrieved for re-ranking, and are essentially we are vectorizing the chunks in real time and then scoring them in real time. In that way, you don't have to process everything as it comes in and cache it, and potentially have to reprocess it again later. So it can be a cheaper way to keep your vectorized version of your data and get semantic scoring. That's why we do it versus caching things in a vector database, which is essentially what's going on with embeddings. And so, but in our pipeline, we have a layout model. In most advanced RAG pipelines, that's true. That has to run on a GPU. And then we are chain prompting, processing our chunks agentically, as I mentioned, and we use our own hosted models to do that as well. And those are, typically something like a Gemma 3.
Gotcha. Can you dig a little more into, so when a document gets uploaded, it gets divided into chunks. If I recall correctly, that is from a detection model. So you have a visual detection model that looks at the page, and that's a model, and it visually breaks things up into chunks, such that it's spatially motivated, not arbitrarily based on tokens or whatever. So that happens, and then those chunks aren't getting vectorized right away. They're getting vectorized. Did I understand on the fly on retrieval?
So so after that happens, it goes through an agentic process, and the agent will do a chain of tasks on the chunks, on the document itself. Actually, there's a main agent process that's doing a document level analysis. Then it passes off its understanding of the document to a section agentic processes that are processing sections of the document, assuming the document's long enough to have sections. That this only happens 20 pages or more, something like that, where there's a section agentic process. Then there's a chunk agentic process, and those are very specific to the chunk types, whether it's a table, figure, or text. And those are taking the understanding that's been developed before it, section and document, and then attempting to create metadata about the chunk that preserves what's contained in the chunk as a standalone idea. When it's retrieved, it stands on its own as a piece of content. And as part of that, there are fields. We create keywords and we vectorize those. So only a subset of the actual chunk text is vectorized and stored. And that's really to help surface it when we do our search later. The re-ranking is evaluating the entire chunk text in real time and creating a semantic score of that chunk. How likely is the answer to be contained in the chunk? It's a paraphrase of what's occurring with the vector calculations, but it's essentially what's when you use embeddings to create a vectorized version of your data, it's doing a part of that process and caching it.
Gotcha. So you have this sort of semantic object that is using a variety of hosted LLMs locally. And if I recall, those are fine-tuned LLMs specifically for this task. So these LLMs are basically looking at these chunks, which are found via visual models, and rewriting them to be more robust for hybrid search. So maybe more traditional search approaches like textual-based search approaches. And then you also have keywords that are extracted, which are vectorized. And then those are kind of maybe a more RAG traditional approach, which is vector search. Then those two together go into getting the specific pieces of information, let's call them chunks, for your retrieval. And so there's a lot of stuff. I think the elephant in the room is, I presume this matters, right? It's necessary to do all this stuff, right? It's if you don't do this stuff, I imagine there's significant drawbacks in terms of performance or something like that.
Yeah, I mean, the short answer is there's all kinds of things that are not explicitly written that are just implied by where the chunk is, whether that's what chapter it's a part of, what book it's a part of. None of that's explicitly written in a chunk. There's a lot of context that surrounds a chunk that's never explicitly written. And that's what we're creating, trying to attempt to recreate when we're processing the chunks. Something that's searchable. These other things that are not explicitly written.
I want to let's jump a little bit to a different topic here on deploying on premises. How do you think about security? And this is probably the number one issue, literally the reason why companies or governments want to deploy RAG on their own premises, their own data center, some environment they control. What are the unique security issues you have to think about when building and deploying a RAG system in an environment like that?
Well, I mean, I think, Neil, you asked me one time how concerned we should be about DeepSeek stealing all our information. And, if DeepSeek's running on a laptop that's disconnected from the internet, I don't see how, even if there were something malicious and hidden in the model itself, it could, do anything unless it could connect itself to the internet. So, being able to run a RAG system disconnected from the internet is inherently the most secure way you could run a RAG system. In a traditional RAG system, very commonly the embeddings are accessed as an API, something like OpenAI's APIs, so that you don't have to deal with the headaches that I've talked about of running an LLM at massive scale. And that making that call out across the internet, even if you trust OpenAI with your data, is it's inherently a risk vector. Any kind of external call out of your system, or ingress or egress in and out of your system is a security risk. And so our goal has been to create a RAG system that runs at scale, every aspect of it most efficiently on the available hardware that's there, and flexible enough to adapt to what's available and run disconnected from the internet.
So are there unique technical challenges to pulling that off?
It's really the models, hosting the models assuming that you've thought through, a well-architected ingest pipeline that has microservices and is flexible enough to maximize the compute that's running the processes, the microservices. Then it's really the models. And again, I think it's the hosting the models and running them efficiently on your own is 60% of the headache of running a pipeline, at least, if not more. It's one new thing in terms of doing compute systems at consumer scale, but it's a very uniquely challenging thing. Having said that, when you get beyond not sending your data to a third party and not connecting your system to the internet, you do have to think about things like data governance, who has access to what. Those are all considerations as well.
Yeah, like how do you think about like role-based access controls in a RAG system? We hear questions about that a lot. I want different people in my company to have different access levels to information that sits in the RAG database, and so they ultimately get different answers depending on what they ask, based on the different information that they're allowed to see or they're allowed to search. In a traditional system, you just don't let someone access a file folder. But this is not like that. So how do you think about implementing something like that with a RAG?
From what I see and what's possible in our system, it's pretty similar solution. You expose a metadata field that gets attached to every chunk and document, and that metadata field can contain whatever metadata you want to store with each chunk and document. People are typically using pre-filter queries to basically filter out which chunks are even searchable based on this metadata field. That does take some amount of engineering. If we fast forward 2 or 3 years, I imagine people will have built plugins on top of this metadata field to some kind of third-party governance, existing governance systems, and you'll be able to manage these things outside of writing code that filters your chunks and ensures that the right governance rules are applied to every document and chunk. But that's currently how it happens and how you would do it with a GroundX. You would use this filtered field. You would pre-filter chunks, not even make them searchable based on what you've stored there.
So every when you ingest a document, I think you're saying when you ingest a document, that document gets tagged in this field with a role, or like what level of access you would need to have.
LDAP rules or some kind of governance rules that already exist.
Right. And then when when someone asks a question, you're basically comparing who they are, what their LDAP rules are for that person, and that would set the filter for which documents could even go into, which chunks essentially could even be allowed into a RAG search before an answer is generated and sent to an LLM.
That's right.
Yeah, so it's interesting. So the security is not at the LLM level. A lot of people may think, oh, you have to implement security with the completion model. You're saying, no. You have to step that way before that. When you even at the search point of search, you don't want any of that coming through a pipeline and getting anywhere near an LLM.
That's right.
What else? What are the other big? We've talked about scaling, a lot about that. We've talked about hosting models, a lot about that. Security, obviously, is the number one thing people come looking for when they talk to us at EyeLevel with GroundX on premises. Are there any other big roadblocks that developers need to know about?
Lots, but
or like what's one weird one people don't think about? Surprising one, because you've been doing this for building the system for 4 years. Like, what was a curveball you didn't see coming, and you're like, oh my god, this is.
Yeah, I mean, the big ones I still see are really thinking through eval. It's a major pain. I imagine you guys have done videos on eval, what eval means, but eval, really thinking through eval, and then I can't emphasize enough how you really have to think about ingesting documents, RAG knowledge into a RAG database is a massive massive problem that creates consumer scale challenges on your system. And if you don't start from that thought, the experience you're going to have is that I'm trying to upload a folder of files and it's taking 2 days to upload. That's how you experience this problem. And the reasons are that it's creating massive load on systems, and you have to think through how to handle that load. To me, those are the two big things that I see out there that people are just not thinking about enough. how to really evaluate how efficiently you've captured the information from your knowledge base and how accurately you can retrieve it. And then how are you going to get, the actual full scale knowledge that you're trying to ingest into a RAG database?
Yeah. All right. Well, listen, a lot of great advice today. I really appreciate it, Ben. Thanks for coming into the RAG Masters. And look, there's a lot more to discuss about how to do RAG on premises. I'm sure we're going to do this again. So hopefully you'll come back and join us one more time.
Absolutely.
All right. So that's good for us. Thanks, everybody, for joining us for RAG Masters. Daniel, last thought. What do you got to say?
Dude, I would not want to be... Well, I'd want to be Ben now because he already did it. Like, that'd be really cool. But I imagine if we told Ben, hey, you have to go back in the past and redo this all from scratch. It seems I have so much respect for people that know the infrastructure and the machine learning and the application development and the networking and the security and the cloud. Like, there's so much stuff that you need to know to do all this together. And I've only met maybe like 5 people that know that much stuff, tops. And I've met a lot of developers. There's not a lot of people that are even capable of this type of stuff. So it's super cool to talk.
And I'm sure not one of them either. So, but hopefully out there, we're helping you guys get a little bit closer to that goal. Stick around. We'll see you next time on RAG Masters.